All right, welcome back from reading break. We are going to pick up where we left off, talking about the F test. Okay, so let me remind you of a few things. So I still have a picture of an F distribution over here, which I'll use to remind you first of the F test for linear combinations of parameters. So recall we have this expression. So recall this hypothesis that we discussed right before the break. Recall the general linear hypothesis. Null. So we have a matrix of constraints A times the parameter vector, testing whether that is 0. So right before the break, we talked about various situations that we can test using this hypothesis. And so if we look back at our notes from last time, we can use this to test whether there's overall any significance in the multiple linear regression. We can use it to test what we call reduced models. So we can, if we take, for example, take away some of the predictors from the model, we ask whether that's plausible. And we can also use it to test if we can remove, for example, some of the categories in the categorical predictor. Okay, so remember that this is a matrix of constraints, and it's going to be of rank L. So the matrix A codes for L constraints. Okay, so the null hypothesis is that these constraints are indeed plausible in what we call the reduced model, versus the alternative, which is that it is not plausible for all of the constraints to be 0, so that this A times vector B is not equal to the 0 vector. Okay, and then we also had the F statistic. Okay, so our F statistic for this hypothesis. So let me just review that. So we have the sum of squares residual based on fitting the model with the constraint. So I put subscript A here. And the key statistic is this difference between the sum of squares. So what's left over in terms of the residual sum of squares after fitting the reduced model compared to fitting the full model. Okay, so we have that. This is a key quantity, the difference. So the additional sum of squares that the full model is able to explain. Okay, so we look at this difference and we divide it by the number of constraints, so average over the number of constraints, so divide by L here in the numerator. And so let's also label this. So this is the, so this part, remember this subscript A means this is from fitting the reduced model. And then this one is from the sum of square residual in the full model. Okay, so also useful to remember here is that when you add predictors to a regression model, the sum of squares residual can only go down. So in other words, the sum of squares regression, or the R squared, can only increase according to our geometric argument, right, from the Pythagoras theorem last time. So when we add predictors to the model, the R squared, or equivalently the sum of squares regression, can only go up, which means the sum of squares residual is going to go down. Okay, so therefore this quantity is always non-negative. Okay, so therefore the sum of squares residual will be smaller when you have more predictors, which is in the full model. Okay, and then in the denominator we have the sum of squares residual from the full model divided by degrees of freedom of the residuals. In the full model is n minus p minus 1, which we also know is simply, so this entire expression is simply sigma squared hat. Okay, and we said that this is the statistic that we use to test this hypothesis, and then we compare this statistic to the F distribution with degrees of freedom numerator L and then denominator n minus p n minus 1. Okay, so this is a example of an F distribution, and because the evidence against the null hypothesis is when this difference is large. So in other words, the fitted models are quite different when you impose the reduced model versus when you don't. So that's evidence that you in fact do need some of these additional predictors without the constraints in the model. And so therefore, when this is large, that is evidence against the null. So when this is large, that means we're on the right side of the F distribution, and so we reject when this test statistic lies in the rightmost alpha in terms of the quantiles of the F distribution. Okay, so that is a recap of last lecture. So now I want to look at a special case and connect what we've done here in this F test framework and connect it to the ANOVA table, which we saw in the lecture before that. Okay, so I will call this a special case, the test of overall significance. Okay, so we're asking overall, are any of the explanatory variables related to the response? So we can call this overall test of significance. Okay, and that also help us illustrate this framework. Okay, so this answers the question: are any predictors related to the response? Okay, so that's the question answered by this hypothesis test. Okay, so what is the null in this case? So the null hypothesis is that none of the predictors matter, and so we can write this in terms of the individual regression parameters in the model. So beta 1 doesn't matter. So we have each of these coefficients. So we have p predictors in general, and if none of them are related to response, then we can write this in as the hypothesis that all of these are simply 0. Okay, so this is the null hypothesis versus the alternative that at least. So the alternative, well, it's the opposite of this. So it's if the opposite of none of them matter. Well, that means at least one of these betas are related to the response. So there's different ways you can write it. So let's just say alternative that beta j is not equal to 0 for at least one j. Okay. So this when the null is true, then none of the predictors are related to the response. So what's the corresponding matrix A in general that can capture this hypothesis? Well, we can indeed write it in this general F-testing framework using the matrix as follows. Okay, so how many constraints are there? Well, we're setting beta 1 equals 0, beta 2 equals 0, up to beta p equals 0. So there are p constraints in this hypothesis. Okay, so we can write it as setting. Okay, so let's write the first one. So beta 1 equals 0. So that means, so remember, okay, just to remind you, we're going to be multiplying this by beta 0, beta 1, up to beta p. Okay, and then the hypothesis is that this multiplication will give you a zero vector. So you write it this way, remembering how these are ordered from beta 0 to beta p, then we can fill in the corresponding entries in this matrix A. Okay, so to encapsulate that beta 1 equals 0, then we have a 0 for beta 0, and then we have beta 1, and then nothing else, so the rest are zeros. Okay, so this row gives us the constraint beta 1 equals 0, and we do likewise for the rest of the parameters. Okay, so the second one is beta 2, so beta 2 times 1 equals 0. Okay, and so you see the pattern. You're gonna get the ones in this in the diagonal here. Well, I mean in the entire matrix. I mean, if you look at this sub matrix, then this is in fact the identity, p by p identity. Okay, so let's finish writing this. Okay, and so as I noted, this part. So this part in red here is simply an identity matrix p by p. Okay, so that's how we can write this overall test of significance in general linear hypothesis form. Okay, so that's matrix A. So when you multiply this times the parameter vector, that's the hypothesis is that this gives a vector of zeros, and that indeed there are p constraints here. Okay, and so if the null is true, then what model do we have? So if the null is true, then that means the model is, that means all the beta 1 up to beta p is 0. So what's left of the model? So the model is yi equals, okay, so you have beta 0, and then usually you would have beta 1 x1 up to beta p xp, but we are hypothesizing that they're all 0, so what's left? Well, all you have left is, well, beta 0, right? So if the null is in fact true, then yi is simply beta 0 plus epsilon I. So that's all that's left of the model. So in fact, or alternatively, you can say that yi is normal, mean beta 0, and variance sigma squared. Okay, so that's all that's left when we remove all of the predictors from the model. Okay, and so what happens in this case? Okay, so I'm going to need to. So remember, this is the F statistic, and then we're going to relate it. We're working towards relating this to the ANOVA table, but I need to make some room here. So let's see what happens in this case. Okay, so based on this F-test principle, we're going to fit this reduced model. Okay, so in other words, we're going to fit the reduced model. Okay, so in other words, we're going to estimate beta 0. Okay, so following this, okay, so we're going to fit this model here. In this case, estimate there's only one model parameter besides sigma squared, so we need to estimate beta 0 using least squares. Okay, so again, this is actually quite simple now because we only have one parameter. So what is this? So minimize. So what we're going to do? Take each data point. I minus, so the mean is beta 0, okay, square, and then sum. Okay, so that's what we're minimizing, and so this is actually a much simpler minimization problem compared to the ones we've seen already in this course. So we can easily verify that using calculus, which it can be shown. The least squares estimate for this very simple model is simply beta hat 0 is x bar. y bar, the mean response. Okay, so let's look at what happens then for the F test when we have in this scenario. Okay, and so what is the sum of squares residual under this condition? Okay, well, sum of squares residual, as we know, is you can write it in different ways. So here's take each residual, square, and then sum. Remember, this can also be written as E transpose E, looking at the vector of residuals. Okay, and so what is the residual here? Well, you do yi minus the fitted value. So fitted value is mu I hat. Okay, square. So that's still in general, but in this case specifically, the fitted value is simply beta 0 hat. So we can plug in y bar for the fitted value. Okay, so that's the sum of squares residual for the fitted model under this constraint. Okay, but so the key thing to connect here with the ANOVA table is to recognize, well, what is this expression? Well, this looks familiar. Y minus y bar squared, right? So this quantity, as we've seen already, is related to the overall variability in the responses, in the yi's, okay? And so this is, in fact, this is n minus 1 times the sample variance of the yi's. And in fact, this is a quantity we've seen in the ANOVA table. This is what we've called the sum of squares total. Okay, so so we know now that when all the regression parameters except the intercepts are 0, then the sum of squares residual under that constraint is simply the sum of squares total. So let's look at what happens to the F statistic. Okay, so then the F. Okay, so in this case, I can substitute sum of squares residual A to be, so just put in different colors so it's clear. So this is now sum of squares total minus sum of squares residual. Yeah, and also remember here that sum of squares total only depends on the responses, right? So sum of squares total never changes when you add predictors to the model or remove predictors in the model. Sum of squares total is only looking at the responses. Okay, it's a function of the yi's only. Okay, so this is the same value under any model that we would consider for the y's. Okay, and so we also now need to fill in the number of constraints. So this is divided by the number of constraints, which is, as we said, this is a p by p. In other words, the rank of A here is p. So because there are p constraints, so let's also put in p here. Okay, so we've now applied the F-test formula for this special case. Okay, and then on the bottom is what we usually have. So this is the sum of squares residual divided by n minus p minus 1. Okay, so this is true for this special case. Okay, so now let's simplify this. So what is sum of squares total minus sum of squares residual? Well, by definition, because of the sum of squares decomposition, we know that sum of squares residual added with sum of squares regression gives us a sum of squares total. Okay, so therefore this is simply sum of squares regression divided by p, and then in the denominator is sum of squares residual divided by n minus p minus 1. And so, well, what is this? Well, these are actually things that we already saw in our ANOVA table. Sum of squares regression divided by regression degrees of freedom, that's actually p. Okay, so this gives us the mean square regression. And on the bottom, well, as we said, this is alternatively called sigma squared hat. It's the estimate of the residual variance, also called the mean square residual in the ANOVA table. And so what was this thing that we said we'd come back to? Well, it is indeed this F ratio, which is mean square regression divided by mean square residual. Okay, so we've calculated that before in the ANOVA table, and now we see its significance. Okay, this meaning is that this is indeed the F statistic used to test whether any of the predictors in the regression are significant. Okay, so now we have explained what the F column in the ANOVA table that we constructed means. Okay, so this guy is the F, indeed the F statistic in the ANOVA table. Okay, and so therefore in the default ANOVA table gives us the information necessary to carry out the test of hypothesis of whether overall any of the predictors are useful in the regression model. Okay, so this summarizes and concludes the discussion of the F test and the special case of the F test in our ANOVA table. So remember that F tests are quite useful. For example, we can use them to help decide which of the predictors are useful to include. Like when we ask questions whether we can drop certain predictors from the model, or whether any of the predictors are useful. As we continue to work through this part of the course, we'll also see how the relationships between predictors, so among the x's, can also play a role. But for now, today I want to do a bit of a longer R demo because I want to show you how to work with this F distribution in R, show you ANOVA, how to construct ANOVA tables in R, and how to carry out this F test. And so I'm going to move over to the computer, and then we are going to run through that for the rest of today's class. Okay, so just give me a moment to switch the camera, and then I'll be back with you right on the computer. Okay, so I have R open here, and so I added one data set to our website. So it's the coffee quality data set that I talked about a couple lectures ago, and so we'll use that and also the existing rocket data, and I'm going to show you these examples. And also along the way, I'll teach you a little bit of a little more of how to use do various things in R. Okay, so the first is sort of a pretty general thing, is plotting functions. Generally, well, when you want to plot a smooth function, well, what we're literally doing is we're evaluating a function along a pretty fine grid, and then we're basically joining the points together. So that's conceptually how we plot a function. So just to illustrate that, so I'm going to use the sequence command here to create. So what this does here in this line is I create the sequence of numbers from -4 to 4, such that
the difference between each number in the sequence is 0.01. So if I run that and look at x, so the first few values are going to be -4, -3.99, and so on. Okay, so this is an example of creating a grid of values for which we might want to evaluate a function. Okay, and so to illustrate this, so I'm going to plug these x values into a function. So as a first example, I'm going to use the density of a normal random variable with mean 0 and standard deviation 1. Okay, and so what dnorm is simply shorthand for calculating the density. So you've used, for example, rnorm before. So norm is the identifier for the distribution. So you put an r in front of it. That's what you've previously used to generate random numbers from a probability distribution. And so d is the function that evaluates the probability density. Okay, so we can evaluate this. So x is a vector, and dnorm is a vectorized function. So it's allowed to put a vector in, and what it's going to do is simply it's going to evaluate the density for every number in the vector. So dnorm is an example of a vectorized function. Okay, so now we've calculated our x values, we've calculated our y values, so we can plot them. So we can use the usual plot x variable and y variable command. And specifically, we want R to give us the type of plot we want is lines. Okay, so we want it to join together all the points and create a smooth curve for us. So that's why we put type equals L. Okay, so we do that, and that gives us the famous bell-shaped normal curve. Okay, so this is the normal density function, and so of course you can change this grid size. So I've just used 0.01, so that's fine enough to give us a smooth picture of this function. Of course, you can also define your own functions. So let's define okay, so let's also evaluate. For example, we can do x squared, or and so here's another. So we can evaluate that. We can calculate our own custom values. Just either type the formula or type the formula and create a function for it. Okay, and so we can also plot y equals x squared with our own defined function in a similar way. Okay, and so the reason I tell you this is, of course, there's a question or part of your homework where I ask you to add a density function to your plots. So this gives you some of the R functions that can help us do that. So specifically now I want to show you some examples of the F distribution. Okay, and so remember, where does the F distribution come from? Well, it is positive valued. Okay, so why is it positive valued? Well, because it is the ratio, is a scaled ratio of two chi-squares. Okay, so you take chi-square with numerator degrees of freedom and then divide it by chi-square denominator degrees of freedom, and then there's the constant, right? We divide both numerator and denominator by the corresponding degrees of freedom. So we end up with a positive random variable. So F can be, so I'm creating a grid for plotting some F probability densities. So I'm going to create, I'm going to plot from 0 to 5, okay, as my x values. Okay, and so similar to dnorm, we also have a density function for the F distribution. So that's abbreviated df. And so syntax is very similar. The two parameters I have to put in the degrees of freedom. For degrees of freedom 1 is the numerator one, and then the degrees of freedom 2 is the denominator. Okay, and so as before, I'm going to use type equals L, so I get a smooth curve. And as we showed you for your first assignment, you can add labels. So I'm just going to call the x label x, and then call the y label density. Okay, so I've now plotted the F distribution with degrees of freedom 1, comma 1. Okay, so it looks like this. Okay, and so what I'd like to do is show you a few different plots of F distributions on the same graph. So I'm gonna show you a few other plotting options so that we can plot all of them on the same graph, and then I can even add a legend so we can identify them. Okay, so I'm going to plot it again. Okay, so I'm going to do the same thing. I'm going to specify a specific color. Okay, so this is my first curve. So I'm going to color it black, which is in fact the default. And just to make things a little more visible, I can change the line width. So that's LWD. So I'm going to use a line width of 2. The other thing I can set in the plot is for example, the limits of the axes. Okay, so I can, in this case, by default, it goes from like 0 to about 3 based on the values. But in this case, I'm going to be adding various other densities to the same graph, so I can also manually set what I want the y-axis limits to be. So you can give it two numbers, the lower endpoint and the upper endpoint. So this vector 0 and 2.5 will give me specify the limits of the y-axis on the plot. Okay, and so let's execute this. So we should see the y-axis change, and we should also see the line be a little wider. Okay, so that's the result. So this sets up the plot. So when I first call plot, it will create a new plot. And now what I want to do is I want to add lines to the plot. And so to do that, I use the lines command, and the syntax for that is very similar to plot. And you notice, in fact, the syntax is almost identical. So we put x values, we put the y values, and then we can also specify the type. We want to draw a smooth curve, and then I can also specify different colors and line widths. Notice, because the plot is already set up, I don't need to put like new X labels or Y labels because I already have a plot, and also we aren't going to put new axis limits. Okay, so that's why we don't have those options in here. So this will add this data I specify as a line on the plot. Okay, so what am I doing here? Well, as my next one, I'm going to do degrees of freedom 1, comma 100. So I'm going to add that to the plot in green. Okay, so you see what happens is basically when you keep you see in this case, when we keep the first numerator degrees of freedom fixed and increase the denominator degrees of freedom, that basically pushes the curve slightly to the right. Okay, and so that's seen here in the green curve. Okay, I'm going to also add a few more. So I'm going to do 5, comma 1, and then 5, comma 100. Okay, so 5, comma 1 looks like this. So one thing that you notice that changes a lot when you increase the numerator degrees of freedom is, rather than asymptoting up, it's going to start at 0. It's going to peak and then come down, which is kind of the shape of the F distribution I drew earlier on the board. Okay. Okay. And so what happens when you take 5, comma 100? Again, we should see it shifts to the right, and including the peak of the F distribution will also shift to the right. So that's added here in purple here. Okay, and so let's also show one more. So let's also do 10, comma 1 and 10, comma 100. So that's the red curve is 10, comma 1, and then as I do 10, comma 100, that's also shift to the orange curve, which is to the right, and then the mode is also further to the right, and the density is more spread out. Okay, so now I have all these different curves. So what if I want to add a legend? So there's a legend command that makes this quite straightforward to do. So the first so you can always look at the help documentation that comes with each function for for all the possible options that you can use with it. So I'm going to put the legend in the top right, so it takes a string in the top right, and then basically I got to label all these colors, right? So I basically here I just labeled, okay, it's 1, 1, 100, and so on. So I have six different legend labels, and then for each one I'm going to color code them according to the colors I used for the plot. Okay, so this legend command adds that to the top right of the plot, according to the text, and also and according to the line type and color that I specified. Okay, so that illustrates, gives you some intuition for what the F distribution looks like for various degrees of freedom. And on the side we show you how to plot multiple things in a single R plot, and so that can be useful for making figures. Okay, so next I want to move on to generating random numbers from the F distribution. Okay, and so just so this code is reproducible, as I often ask you to do on homework, set the seed first. So I'm just going to use this number 1, 2, 3, 4, 5, 6, 7, 8. Okay, set that seed, and then we're going to generate some random numbers. Okay, so just like we've used R norm, I'm going to use RF to generate some random numbers from the F distribution. Okay, so I'm going to generate 1,000 of them, and I'm going to use one of the scenarios we have up here. Okay, so I'm going to do 5, 100, so that corresponds to this purple this purple density curve that we've already drawn. Okay, so let's simulate some random numbers. So let's store it in this vector. I've called it randf. Okay, and so histogram. So that's the next thing I wanted to show you. So histogram, you probably know what it is, conceptually at least. So basically it takes a bunch of numbers, and then it draws bars on the plot corresponding to how frequently you see those numbers in various ranges. Okay, so there's a default function for that in R. It's called hist. So it takes as input a vector of numbers. Okay, so here I'm going to plot histogram of these random numbers I just generated. Okay, so it looks like this. Okay, so in other words, there are about there's about 200, little over 200 values out of the 1,000 that fell between 0 to 0.5, and there's about a little more than 350 numbers from randomly drawn from the F distribution that fall between 0.5 and 1, for example. So here by default, the histogram shows the actual number of the frequency. So you notice like all these bars add up to 1,000. Okay, I can also change it to relative frequency. So to do that, I want to set frequency equals false, so that will convert the scale from frequency to relative frequency. So I plot that again. You notice it'll now call the y-axis will be called density to denote that, for example, just over so this is now normalized to mimic a density function. Okay, so it takes all the values and such that, for example, if I were to superimpose a density on top, a probability density on top of it, the scales are going to be the same. Okay, so what I'm going to do is, well, I'm going to now add a density curve corresponding to the F distribution from which I drew these numbers. Well, now that we've learned how to add a line to a plot, I can add a line to this histogram plot as well. So I'll use the lines command. In fact, I'm going to do exactly the same command I used up here to add the F density function with degrees of freedom 5, 100 on top, and superimpose that on top of this histogram. Okay, so I can do that, and then you notice now I have this this purple curve. Okay, so I can make this plot look a little nicer. For example, you notice it does, remember the y-axis limits don't change when you add things. So you notice this purple curve got cut off a little bit here. So let's do a few things to tidy this up. So what I can do, for example, is change the y-axis limit, so make it a little higher, so this plot doesn't go off the limit. And what I can also do is, well, I mean, by default, the histogram, it's not particularly fine. It's using bin sizes of about 0.5. So I can create more detail in the histogram by changing the number of breakpoints. So here, for example, the x-axis goes from 0 to 5. So if I use 25 breaks, then that means instead of having 2 bins per unit here from 0 to 1, I will have 5 bins. And so R doesn't uses this as a guideline. Sometimes it won't give you exactly, for example, 25 histogram bins, but it will give you something that's close to that. So there's a question, which is the x value used in the lines function operating on the x that was predefined above? Yes. So I had defined, yes, so I'm still using the same definition of x for the grid of x values as when I started the F distribution example. So I'm still using the same x here. So yes, this is still the sequence from 0 to 5 with intervals 0.01. Okay, so let's make this plot, make it look a little nicer. So I think it'd be nice to have a little more detail in the histogram and then also change the y-axis limits. So that's why I put a new y-axis limit, 0 to 0.8, and then use approximately 5 bins per unit. Okay, so this is the histogram with 5 bins per unit on the x-axis. So this does give us a little more detail in the shape of the values we generated. Now, because we indeed generated these F random values from F5, 100, so in fact, if we use more and more random samples, this should get us ever closer to the true density function, which is the purple line. So let's add this on. So indeed, this the true density function follows the histogram pretty well. And in fact, if I were to generate, for example, more a larger sample of F values, this should get closer. Okay, so let's just for example do let's do 10 times as many, and we can do another plot. Okay, so let's show you that. Okay, so the histogram, as you see, is a lot smoother now and follows the true density even closer. Okay, so that illustrates how we can do histograms. Okay, so it introduces R, how we can plot histograms in R, and then we can combine it with what we just learned about adding plotting functions on top of histograms. Okay, so in this case, of course, the F this F density and the histogram will agree because they come from the same distribution, but this is one way, for example, to assess whether in fact, at least visually, histogram agrees with, say, a probability distribution that we hypothesize for the histogram. Okay, so with that done, let's now move on to ANOVA. So I'm going to revisit the rocket example. So let's load it in first. So again, remember that this was the example where we're trying to predict thrust from the nozzle size, so either large or small, 1 or 0, and then the propellant to fuel ratio. So that's there were two predictors. Okay, so in that example, we fitted the multiple linear regression model of thrust to these two predictors, nozzle and propellant ratio. Okay, and so we've already seen before the summary table. So you take if you apply summary to the fitted regression, so we've seen this in several contexts now, and I want to relate that now to to the corresponding ANOVA table. Okay, so we've seen this example before where we see that nozzle is highly significant for predicting thrust, whereas it looks like the propellant ratio is not significant, at least by this by looking at this t statistic value. Okay, but the main thing I want to illustrate here is how to construct the ANOVA table. Okay, so on the board I wrote down the values for the ANOVA table for this rocket example in the lecture on October 5th. Okay, so I can now going to use ours ANOVA command to show the table that R constructs by default when I plug in ANOVA. Okay, so I apply ANOVA on the fitted model. And it looks like this. Okay, so this gives analysis of variance table, and you notice it looks a little bit different from the one that we've been talking about. Okay, so the one we've been talking about, we have a regression row and then we have a residuals row. But what R does by default is it separates each component in a regression and gives it its own row. Okay, so in fact the statistics it gives you here are for the individual predictors. Okay, so this is useful for seeing how each of the individual variables are related and their individual sum of square. So for example, these F values here, you notice are very similar to the ones given in the summary table. So how do we take this ANOVA table then and construct one of the form that we've been talking about in terms of having all the regression together and then the residuals together? Well, basically what I have to do is simply combine these two rows in the ANOVA table. So to do that, mainly the key thing I need to extract is the sum of squares. Okay, so once I have the sum of squares for the regression, we can easily fill in the other components. Okay, so we can calculate the mean square and then the F statistic from there. Okay, so one convenient way to get that is the ANOVA. So after you execute ANOVA, it has an attribute called sum of squares. So this is how you access it. So in fact, I can get these three numbers here as a vector of numbers for the sum of squares, three sum of squares values here. Okay, and so if I want to calculate the sum of squares regression, that means I need to add up the sum of squares for the nozzle and propellant ratio. And so I can add together the first two elements of this vector. So I'm here indexing and I want to extract the first two numbers in this vector because this corresponds to the sum of squares for nozzle and propellant ratio. The last one is the sum of squares regression. Okay, so I get the regression sum of squares is 846.2, which is the number I showed you in the lecture on October 5th. And then finally, we can also get the sum of squares residual, and that's the last number in this vector. So that's the third number in the sum of squares vector. Okay, so that's 63.4, as I showed you in the earlier demo. Okay, and so remember this sum of squares residual is really crucial for doing F-tests. Okay, so to illustrate, let's do the F-test of overall significance here. And so I'm going to have to fit a reduced model. So that means fitting a reduced model where we don't have any predictors, we only have the intercept. Okay, so to do that in R, I can drop both predictors and I still want an intercept. So to do that, I actually just put the number 1 here. So R will then fit the model with just the intercepts and omit both of these predictors. Okay, so I'm going to call that the reduced model. So I'm going to fit in a reduced model. And likewise, I can calculate or show the summary of this model. Okay, so it's very simple now because there's only the intercept, which, as we said, the estimate for beta 0 when you don't have any other predictors is simply y bar. It's the average response. So that's 476.6. Okay, and then likewise I can do an ANOVA on this, and notice that R realizes there are no predictors, so it only has a residuals row, and it has 11 degrees of freedom because there are 12 observations in the data set. So this is now just n minus 1. Okay, so let's carry on and do our ANOVA F test for overall significance. Okay, so to do that, we need the sum of squares for the reduced model. So following the notation, I'm going to call it sum of squares residual underscore A because this applies the constraints that both beta 1 and beta 2 are 0. Okay, and so if I want the residual sum of squares, so notice now there's only one sum of squares value. So, okay, so for example, the sum of squares vector only has one number now because there's only one, there's only the value for the residuals. So I can extract that. It's using a similar way. Take the sum of squares vector is the first value now, so that's the sum of squares of the residuals for the reduced model. Okay, so now I can calculate the F statistic. So how many constraints did I impose? Well, I set beta 1 and beta 2 to be 0, so that means 2 constraints. So L is 2. N is the number of observations in the data set, so that's you can either look at the number of rows of the rocket data set, so or look at the dimension of the data frame. So indeed there are 12 rows, and we have 2 constraints, and P is the number of predictors. So we started with 2 predictors. So the reason I'm writing it all out here is so then when I calculate this F statistic, it matches the expression I gave you on the board. So we're going to take the difference between the sum of squares in the reduced, the residuals for the reduced and the full model, divide by the number of constraints, and then divide by, on the bottom is simply the mean square residual. So I calculate the F statistic in this way. So we see that it's 60.04. Okay, and so where have we seen that before? Well, in fact, this is exactly the number in the F column in our ANOVA table. And in fact, if we look at the summary of the model again, so if we go back to the summary of the full model, which I think I called M1, 60, so this number, 60.045, in fact, matches the overall F statistic. Okay, so in the summary output for the multiple linear regression, the F statistic for the overall regression is given on the very last line of the output. And so that's 60.05 and matches the manual calculation that we just carried out. Okay, and R, you notice here also lists the corresponding degrees of freedom. So it's L comma n minus p minus 1. Okay, so in fact, this matches up as we would expect. So L is 2. So the F distribution we compare to is 2 comma 9, because 9 is n minus p minus 1. And then R also gives us the p-value associated with this overall test of significance for this F statistic. Okay, so the p-value here is the probability that the F statistic, in this case 60.05, compare this F statistic to the to the F distribution with degrees of freedom 2, 9, and look at the right tail. So I can also manually calculate that by taking the right tail. So I take the quantile of the F. I calculate 1 minus so this tells me the probability that the F distribution will be less than or equal to 60.05 coming from F distribution 2, 9. Okay, and so that's to the left of it, and we want the right tail for the p-value. So the probability that the f will exceed this value of 60.05, and so we can also manually calculate that p-value, and that indeed matches the p-value given by R. Okay, so that shows how you can manipulate the output of ANOVA and summary given in R to calculate the statistics that we need to carry out F tests. So the second example I want to do comes from the coffee data set that I have been mentioning a couple of times. So this is basically coffee experts evaluating a bunch of Arabica coffee beans. So I've posted this data set on Learn. It's coffee Arabica, so you can let's load that into R, and let's use this for our second example. Okay, so the one helpful thing for this example is that I have a categorical variable, which is the processing method. So if you recall, there were three levels for that, namely wet, dry, and semi. So that's the first column in this data set. So it's given to you as a string, which tells you which of the three processing methods was used for that sample. Okay, and then you have all these measurements recorded by various experts who taste and test these beans. Okay, so there's a bunch of variables here. So in our example, we're simply going to focus on, let's say, flavor as the response, and then we have all these. We're going to treat all these other things, so aroma, aftertaste, acidity, and so on, as predictors. Okay, so first let's fit the full linear regression model, treating flavor as the response, and then using everything else as predictors. So what I want to point out here is, well, all these are numerical, and so we know how to handle numerical predictors. We just put plus signs in between each of them. But we do have a categorical one, and that's processing method. So we can explicitly tell R to create indicator or dummy variables corresponding to a categorical one by wrapping it inside the command factor. Okay, so when we do that, this will oops. So if I do it individually, I need to put coffee here. Okay, so it'll basically code. So it'll tell you that indeed there are three levels: natural and dry, semi-washed, semi-pulped, and then the last one is washed or wet. Okay, so it detects that there's three different levels or categories of this variable, and then when you put this into the regression model, then this will create indicator variables. So remember, we talked about how to handle categorical variables a while ago. So when there are k categories, we need to create k minus 1 indicator variables. Okay, so we can treat one of them as a baseline relative to the others, and then we'll need indicator variables 1 or 0 to code each of the remaining categories. So R can do all of that for us automatically when we put a factor into our regression model. So in this case, since the factors or the levels of the categories here were coded as strings, in fact, you don't explicitly need to put factor for R to recognize these as categories, but it's useful to know this command. For example, if for example the data was coded that, for example, you have like 0, 1, and 2 corresponding to the three categories, then we would need to explicitly put factor, otherwise R would consider them to be simply numbers, right? So if R sees the codes 0, 1, and 2 in a column, then it'll by default just treat it as numbers. We want to treat them as categories. So if we put a factor around it, then R will know to treat them as categories and create indicator variables for that. Okay, so it's helpful to know this in general because not all data would necessarily be coded with strings. There might be they might be coded as numbers, and then there might be some data dictionary which tells us like which category each code stands for. Okay, so this is a useful command to deal with categorical predictors. Okay, so with that said, let's fit the model. So I've called it M full as our full model that has all of these predictors. Okay, so let's look at the summary again. Okay, so this is, let me create a little more space here so we can see everything in the summary together. So here's the table of coefficient estimates. Okay, so notice, so everything is, we have everything as expected for the numerical predictors, aroma, aftertaste, and so on up to moisture. But let's mention what R does when we have categorical variables, which R has automatically converted into indicators. So these two rows here that I've highlighted. Okay, so what this says here is R has taken the semi method and coded that as the first factor, and has coded the wet method as the second method. Okay, so just by reading the R output here, we can decipher which one R treated as the baseline. So there were 3 categories, and so we need indicator variables for 2 of them. So now we observe that this first row is the indicator for the semi-washed method, and the second one is the indicator for the wet method. And so therefore, we now understand that R has treated the dry method as the baseline. Okay, so for example, remember to interpret these coefficients. So the difference between dry and wet is estimated, for example, to be minus 0.03 is the estimate for the average difference between the wet and dry methods. Okay, so that's how we can tell how R handled the coding of these 3 categories. Okay, and so likewise, the estimate for the difference between dry and semi is this number here, minus 0.001. Okay, and so let's just take a quick look at these the significance of these individual predictors, because often that gives us some indication for example, which variables could plausibly be removed, for instance, from the full model, because they're plausibly not significantly related to our response. Okay, so it looks like, for example, here, the difference between dry and semi-washed is likely not to be significant. Okay, p-value is very close to 1, and the t-statistic is very close to 0. And you also look down these numbers, for example, uniformity and moisture, according to the individual t-statistics, don't appear to be significant, for example, at the 5% level. Okay, so let's carry out these hypothesis tests. So I'll give you 2 examples. So just like before, we can use the ANOVA command. So as we mentioned, R will separate everything. Oops, I need to calculate on the wrong spot here. So I need to calculate the ANOVA for the full model. So as we mentioned, R will separate rows for every single predictor here. Okay, but for the purpose of our hypothesis test, so to illustrate the F-test, the key one we need to extract from the ANOVA output is the sum of squares residual. So you notice we have 10 rows here, so I can extract the sum of squares residual as the last number here is 24.264. So that's the sum of squares residual for this, what we'll consider as the full model. Okay, so now let's look at two examples of f-test. Okay, so as my first example, I'm going to consider a reduced model where I'm going to drop out these two predictors, uniformity and moisture. Okay, because it appears from the individual t-tests that they're likely possibly not significant. So let's formally test that. Okay, so the hypothesis test, in other words, is to set their corresponding beta. So in this case, it's actually number of predictors is 10 actually, because I have, okay, I see. So I have 9 variables here, but there we create 2 indicators for the 3 categories here. So technically I have 10 beta. So to be more precise, we're testing the last 2. So it's beta 9 and beta 10. Okay, so testing beta 9 and beta 10 equals 0, so we're setting two constraints here. Okay, so what we have to do is calculate the sum of squares residual for the reduced model, so under this constraint. So first we fit the reduced model, so I'm going to call this the fitted model reduced under the constraint. So I've dropped the last 2 predictors, which corresponds to setting these 2 coefficients to be 0. So fit the reduced model, and then as usual I can look at the summary for that, and also the ANOVA for that. And so the key number to extract here is the sum of squares residual under this reduced model, which is 24.387. Okay, and so now, because I dropped 2 the predictors, this is now the 8th value of the vector. So this is the sum of squares for the reduced model. Okay, so the sum of squares residual is about 24.4. Okay, so with those, I can now carry out the f-test. So I have set 2 constraints. Okay, and then the number of observations is the number of rows in the coffee data set, so it's n. And then I have a total of 10 predictors because I have 2 for the 3 predictors, 2 indicators for the 3 categories, and then we have 8 numerical predictors for a total of 10. Okay, so I'll calculate the f statistic using the formula we shown on the board, and then the corresponding p-value, which is the probability that this f random variable, if the null hypothesis is true, exceeds the f statistic calculated. So the right tail, so 1 minus the CDF up to this f statistic value, which happens to be 2.82, and then p-value is 1 minus the CDF of the f random variable up to 2.82. Okay, and so the p-value is 0.06, which, if we use 5% as the significance level, is not significant. So therefore, to draw conclusions from this f-test, we would say, well, it appears that we do not reject the null hypothesis at, say, the 5% level. Okay, so we don't reject the hypothesis that the regression coefficients for uniformity and moisture can be plausibly 0. Okay, so that carries out the f-test for this particular reduced model. Lastly, I also want to illustrate, well, what if we, okay, so if we look back at the summary for the full model again, so this, I think I call it M full. Okay, so here we also notice one other thing is that it appears that this category, so this semi-washed category, doesn't appear to be very different from the dry method mean by much at all. It appears semi and dry are pretty similar, right, in their estimated mean response when we hold everything else constant. Okay, so for example, what if we want to test whether indeed those two categories can be plausibly the same? Well, to do that, so we want to start dropping categories. Well, one way to do it is to just recode a new variable. Okay, so so I'm going to show you this how we can manually, for example, code indicators. Okay, so this is something we can do here. So we can use the if-else, and so in this case, I want to code dry and semi together. So suppose we want to code dry and semi together and code both of those categories as a 0, and then code the remaining one, which is wet, the wet method, and code that as a 1. Okay, so I can use this command to do that. So the key components here is I use the if-else. So basically, you can put in a vector here, and so if this condition is true, then I'm going to create a vector that's either in this case either 0 or 1, depending on whether this condition is true or not. So for all the observations where the coffee processing method is in either the dry or semi category, I'm going to code it as a 0, and otherwise I'm going to code it as a 1. Okay, so this is one way to create our own variable that combines dry and semi together as one category. Okay, so I'm going to do that, and I'm going to add that to our coffee data frame as a new variable. Call it method 2. Okay, as a method reduced to 2 categories. Okay. So this is how we can manually code this indicator, and of course you can do other things. And so this the reason I did it this way is so I can also demonstrate this in operator. So you can always have a vector of in this case categories, and it's going to be true whenever the processing method string matches one of these. Okay, so this in operator can be quite helpful for that. Okay, and then another way I can do it, for example, just to illustrate, I could also okay, so if I'm just creating let's say I can do a similar way. You can also create an indicator for wet, so in this case, we just need to you can just test for equality. So then you don't need an in command, because you're just asking whether the processing method is wet. So I need to just copy okay, so let's copy this string here. And so this would be another way to okay, so I just need to fix this 0, 1. Okay, so if I just want to ask whether it's wet or not, then this would be an example of a way to code the indicator. Okay, and so it will give me a vector of 0 and 1s corresponding. So of course, based on what I've done, of course, these two are, of course, they're just the reverses of each other, right? So in the way I've coded it, it's going to be 0 for dry and semi, and 1 for wet, and then this just does the reverse. So this will code 1 for wet and 0 for otherwise. Okay, so just wanted to show you both so that you can see how to code up manually code up indicator variables. Okay, so with that done, let's fit the reduced model. So instead of doing factor of a processing method, I'm just going to use this new variable I've defined. So of course you could use either of these because this one's going to, if I use the method 2 variable, that's going to treat dry and semi as the baseline and estimate a coefficient for wet. And then if I use the alternative, use the wet variable, then it's going to treat wet as 1 when it's wet, and so the baseline is semi and dry together. Okay, so I'm going to use the method 2 variable I've defined and fit a reduced model. Okay, again, we can look at the summary. And so now, how do I interpret this estimate? Minus 0.03 now is the estimated difference in the mean response between, so 0 is dry and semi. So this is the estimate for wet. Okay, so the estimated difference between wet and the other two methods is that wet would be lower by smaller by 0.03 if we hold everything else constant. Okay, so this shows you how we can manually code variables, for example, to test hypotheses where we remove a category from the categorical variable. Okay, and so again, we can do the ANOVA, and so now there's only one degree of freedom here because it's just a binary category, and then the sum of squares residual is still the 8th number here, so let's extract that. Okay, so that's 24.388. Okay, and so now we can do the corresponding F test. Okay, so three constraints because I have now set the betas for dry and semi to be the same. So I've removed one of those coefficients. Okay, so in fact, in the earlier indicator coding, that would be beta 1 equals 0 in the original regression. And then I've also set moisture and uniformity to be 0, and so I'm going to correct that. These are the originally were the 9th and the 10th betas. Okay, so we'll do the F test. So the rest is the same. We just have a new value for L, and we have a new value for sum of squares residual for the reduced model. So we use the F statistic formula, and we can calculate the corresponding p-value. So we get these results, which is pretty similar to what we had before. Again, it is plausible, according to the data, that the null hypothesis of removing these 3 predictors from the model is plausible. Oh, I see. I forgot to set L to be 3, so my numbers are a bit off. So let's just run that again. F statistic is smaller because the average. So you notice the reason the F statistic went down and is smaller than the other one is because we're taking the difference of the sum of squares and we're dividing by the number of constraints, right? So in fact, when we're removing a variable that is very non-significant, in this case the beta corresponding to the difference between dry and semi. Okay, so that was very so the sum of squares for that variable is very small. So in fact, the average sum of squares difference over the 3, now we have 3 betas removed, actually went down. So that's why the F statistic is actually smaller in this case, because dividing by L here. Okay, and so the corresponding p-value is actually going to be a little bit bigger because the F statistic is smaller. So indeed, the p-value is 0.13. Okay, so that's why the this F test, as you notice, can be sensitive to which sets of variables that you remove from the model. Okay, and so therefore, in practice, we may carry out several different F tests, but when we move to the more general case where we ask, okay, we have let's say a whole bunch of predictors, which ones should we actually put in the model? So if we want to do that in more generality, we're going to look at, that will require looking at what we call variable or model selection methods. So we have a systematic way of choosing which are the best variables to include in the model, and that's something we'll be working up towards. For now, what we do have is the tool to be able to test any general hypothesis concerning groups of parameters, let's say removing a group of parameters from the model and asking whether that hypothesis is consistent with the data or not, and carrying out the appropriate F test. Okay, so that's the main takeaway. So now you've seen the theory behind the F test, and now we've shown how to do it in R on a few examples, and I've also shown you a little more R coding so that you can carry out the computations you need for your homework, and also continue to develop your skills in using R as we go through this course. Okay, so I think that will wrap up today, and I will just pause for a moment to see if there are any questions about anything I talked about today. Okay, and then as soon as we're finished the stream, I will upload this R file onto Learn, so that you can walk through it and verify what we've done. And the copy data set is already posted on Learn. Okay, so I don't see any questions for now in chat. So let's call it a day, and then I'll be back on stream on Wednesday morning, where we're going to talk about relationships between the x the predictors. So the x among the x variables, what happens when x variables are quite correlated with each other, how they affect the regression. So we're going to talk about multi-collinearity when we come back on Wednesday.